Okay, let's dive right in. What if I told you that we could revolutionize industrial chemistry, make it safer, cleaner, and more efficient, all with a solution that's inspired by something as simple as a soap bubble in water? Well, that's exactly what we're going to explore today. A tiny, self-assembling sphere that just might solve one of chemistry's biggest environmental nightmares.
And this really gets to the heart of a huge question for all of us. I mean, think about it. Everything from the phone in your hand to life-saving medicines is built through chemistry. So how do we keep innovating and building our world without, poisoning our planet in the process?
To really appreciate where we're going, we first have to get a handle on the problem we're trying to leave behind. And that means facing chemistry's pretty toxic legacy.
So here's the deal. For decades, modern manufacturing has leaned heavily on these things called organic solvents. And as you can see on the left here, the whole process uses a ton of energy and pumps out a steady stream of toxic waste. We're talking serious, long-term environmental damage. So the obvious question is, right, why not just use water? I mean, it's cheap, it's non-toxic, it's everywhere. And that question brings us right to the fundamental roadblock in green chemistry. It's the classic oil and water problem. Chemists call it the hydrophobic bottleneck. Here's the bottom line. The molecules we absolutely need to build everything from drugs to plastics are organic, which is basically a fancy way of saying they're oily. And they just flat out refuse to mix with water. It's this one simple problem that has locked industry into using nasty, toxic solvents for years and years.
Which brings us to this brilliant metaphor. To make water work, we can't just brute force it. We need a clever way in. We need, basically, a chemical Trojan horse to sneak these essential water-hating molecules into a water-based environment and trick them into reacting.
And believe it or not, that Trojan horse, it already exists. It's this incredibly elegant, microscopic solution that nature itself has been perfecting for millions of years. So let's meet the hero of our story, the micelle. The secret weapon here is a very special kind of molecule with, you could say, a split personality. The technical term is amphiphilic, which comes from the Greek word for both. And that's because it has one part that absolutely loves water and another part that's terrified of it. So how does this work? It all starts with this one little molecule. See the blue sphere? That's its head, and it's hydrophilic. It's totally happy to hang out with water molecules. But that long green chain, that's its tail, and it's hydrophobic. It wants to get away from water as fast as it can. Now here's where the magic happens. You put enough of these molecules into water, and they do something amazing all on their own. They spontaneously self-assemble. The water-loving heads form a protective outer shell, and all the water-fearing tails tuck themselves inside, creating this perfect little oily core. This tiny sphere is a micelle. It's our Trojan horse. But they don't just form gradually. And this is so cool. This graph shows what happens. At first, the molecules just float around. Then they start lining up at the surface. But once you hit a very specific concentration, the critical micelle concentration, the surface is totally saturated, and then bam! They suddenly just snap into these perfect little spherical nanoreactors. It's not a slow process. It's like a switch just flips on. And once that switch is flipped, these nanoreactors are incredibly powerful. First, they encapsulate those oily ingredients, pulling them into their core. Second, they concentrate them into a tiny space, which makes reactions happen way, way faster. Third, the shape actually helps orient the molecules perfectly. And finally, that outer shell protects the whole reaction from the water outside. It's literally a perfect, self-contained chemical factory. So this technology is amazing, right? But, and this is a really big but, the molecules that make it possible, which are called surfactants, are not all created equal. Their history is really a story, a journey from a toxic past towards a truly green future. We can really break this down into 3 distinct eras. First up, we had the synthetic surfactants, which came from petroleum. They worked, but they were pretty toxic. Then came the designer era, where chemists engineered specific molecules for specific jobs. Super efficient, but also pretty expensive. And now we're finally entering the ultimate era, bio-based surfactants. Now, those first-generation synthetics were a crucial proof of concept. They showed the science worked, but the trade-offs were just awful. These things break down into other chemicals that are highly toxic to aquatic life. We absolutely needed a better way. So chemists got smart. They started building custom surfactants, like molecular architects. A fantastic example is a molecule creatively named Kool-Aid, which is built from vitamin E. It's engineered to create the perfect little reaction pocket. I mean, it's brilliant chemistry, but it's still a synthetic and often very costly process. Which brings us to nature's solution. And this is the key takeaway you have to get. Biosurfactants are not some eco-friendly compromise. They are not a weaker alternative. Through millions of years of evolution, plants and microbes have developed molecules that are often structurally superior to anything we can cook up in a lab. They're more efficient, more robust, totally renewable, and 100% biodegradable. This chart just says it all. I mean, look, on environmental impact, bio-based is the undeniable winner. For efficiency, that's how little you need to kick things off. It's exceptional. But the most stunning number here is the micelle size. That's the actual volume of your nanoreactor. Bio-based surfactants can create reactors that are huge, dwarfing the tiny ones from synthetics. What does that mean? It means you can run bigger, more complex reactions. It's not just greener. It's a bigger, more powerful factory. Okay, this all sounds great in theory. But does it actually work for the kind of complex chemistry our world really depends on? Well, the proof is in the results. The future is definitely aqueous, and seeing is believing. This slide shows 3 real-world examples that prove this technology is a game changer. In this first one, we're looking at a Nobel Prize-winning reaction. Now, it has a fancy name, but all you need to know is it's absolutely fundamental for creating new drugs and electronics. And here, a designer surfactant lets it happen cleanly, in water, at room temperature. No toxic solvents needed. And it gets even more elegant. In this second example, the solution is a simple biosurfactant from a plant, a lemon extract. Seriously. It's being used for another key industrial reaction. But here's the brilliant part. The extract doesn't just form the nanoreactor. Its natural acidity also acts as the catalyst for the reaction. It's doing 2 jobs at once, with an incredible 96% yield. And finally, this third example really hits home. It shows the synthesis of pyrimidines. These are the molecular backbones for so many essential medicines that people rely on every single day. And here, a biosurfactant made by microbes does the heavy lifting, pulling the ingredients into its core and allowing this vital chemistry to happen in pure water. This is how we start building a greener pharmaceutical industry from the ground up. So the big takeaway here is crystal clear. The era of just defaulting to toxic petroleum-based solvents is coming to an end. We've proven that with the right key, with these incredible micellar nanoreactors, water isn't the enemy of organic chemistry. It's actually the ultimate green medium. This whole story proves that high performance, precision, and sustainability can absolutely go hand in hand. And it leaves us with this really fascinating question. If we can solve one of chemistry's biggest pollution problems by just looking closer at a bubble, what other massive, world-changing challenges could we solve by studying nature's tiniest and most elegant designs?